this is basically what MKL provides, the feature set, basically. Well, first of all, there's, of course, BLAS, basic linear algebra subroutines. Everything that's connected with multiplying vectors, multiplying matrices and vectors, and multiplying matrices and matrices. This is the BLAS levels, 1, 2, 3. So this is all very highly optimized, what we have here. Additionally, there's a sparse BLAS implementation that we provide. And of course, the linear algebra package, all the solver functions, eigenvalue solvers, Cholesky, whatever. Everything you desire, everything you know from LAPACK, we implement in this library as well. Standard calling interface, no problem. Then there is a scale APAC for distributed memory architectures. So I have a couple of workloads requiring that. It's quite nice software package. Of course, there is FFTs. And I'll just mention it later on again. There's also, so we implement our Fourier transforms ourselves. However, we have interfaces into the other public and most publicly accepted fast Fourier transformation package, which is FFTW. So we provide an interface package into FFTW, which calls our internal Fourier transformation. There is a cluster FFT solution, which I will not speak too much about. And there is this dense, sparse matrix solvers, Perdido, DSS, and ISS that we also supply. In the MKL is also a VectorMouse library. This, I think, also already comes with a compiler. If you use our compiler, you already have a vectorizable mouse library. Often leads a little bit to irritations because this will essentially call vectorized versions of exp, power, zenus, and so on. There's a vector statistical library. This is basically, mostly of it is a huge collection of random number generators. And you don't generate random numbers piece by piece, you generate streams of random numbers. And if you have written a Monte Carlo, you know that random number generation can be a performance critical issue. You sometimes spend more time in generating the random number than actually doing the step. So this is quite nice for that. There's also a summary statistical library that allows all kind of statistical computation like skewness and kurtosis of matrices and so on, error calculations, all these kind of things. There's a component that does data fitting. It does all kind of splines and all these things, and everything nicely tasked and so. There's a number of solvers for partial differential equations. These guys actually do exactly what we tried to program in intrinsics. It does Poisson equations. It does Laplace equations. These kind of things. You can basically, if you have like the wave equation is nothing like a twice time-dependent Laplace equation, so you could wrap this into one of these solvers. Right, so that's essentially it. Okay, we support that for, of course, all possible data types, single real, complex precisions. It's available for C, C++, and Fortran mostly. For some packages, the Fortran interface is the natural one, like LAPACK. And there's access via a function library called CBLAS, which allows the access to these functions from C. Of course, like on the Intel Web Page, you find all nice knowledge base and forums and documentations. I think there's even a full forum about MKL. Quite popular. Okay, and this is minimum interesting. Okay, so now the components in detail. I already talked about that. All BLAS levels, of course, are highly vectorized. This is important for us internally because we try to reach peak performance on the BLAS, and this is a critical component for most deals, essentially LinPack on all these kind of things rely on our performance in MKL, especially the level 3 BLAS. The matrix operations are essentially very critical. As I said, sparse BLAS is fully supported. There's a full packed and banded storage of matrices, and of course the corresponding routines to actually solve that. Well, this is actually the explanation of what we would have done in the hands-on. This is a matrix multiplication. Right? That's very nice. A lot of people write it that way. This would be an implementation in BLAS level 1. D dot basically means a scalar product between two matrices. So you do square many scalar products. Then essentially from the BLAS level 2, you can wrap that further back into matrix vector multiplications. And then you basically have n many matrix vector multiplications. Or if you just do away with anything, you just have the function dgem, which does the whole thing. So this is essentially what dgem does. Of course, it doesn't do it this way. It does it in a very nice cache-blocked way, so you get top performance out of it. Don't expect, and we had this, this case recently, exactly here, don't expect performance out of matrices smaller than, say, 12. Because for small matrices, this is not going to work. This is set up for bigger matrices. Close to peak performance, like reasonable fractions of peak performance, you get with matrices in the order of hundreds and thousands. Right. LAPACK, anybody highly depending on LAPACK and BLAS? A lot of people actually should use that. Nobody has a linear algebra problem? Top 500 is not exactly a problem, actually. It's a nuisance. Okay, so I thought that this is fascinating. No iterative solvers, something like that? Or top 500 is just matrix multiplication. It's just a, oh, this is good, okay. Huh?
The director of the site actually has a problem that is heavily utilizes the gem from a short distance.
Oh, good to know. Well, he should be happy with dgem, actually, with our gem. Okay. Okay, so basically MKL supplies everything that's in LAPACK. LAPACK is a pretty extensive set of solver and utility functionalities. Everything that's, so for my personally, I usually do that with eigensolvers, and they are pretty nicely performing on MKL. Additionally to that, we have kind of, what's really cool, we have callback functions. We put that in, so software vendors that actually run through a big calculation could actually feedback into the GUI of the user where they are. How much do we still have to do? That's why there's a callback function. So you can basically get a feedback on where the computation currently is. The whole of that is actually, if it is possible, it is parallelized completely. So all of BLAS, of course, is fully parallelized. So if you give MKL a node with a number of cores, it will fully utilize that node whenever it's possible. It would, by default, just do it.
How do you give it a node?
You just started. You link it. So, okay, that's a very good question. Okay, so you can control. Let me just jump here a little bit to the environment settings. All right, so essentially it would read out these variables. All right? OpenMP num threads and MKL num threads must not be the same thing. You can set MKL num threads, and it will use those num threads, which can be different from OpenMP. You can have many OpenMP threads, like say 8, each using 2 threads on MKL. That will work. So you have OpenMP num threads. If you don't set MKL num threads, it will just use the OpenMP num threads. If you set MKL num threads, it will use MKL num threads. So that could be, that's, if you don't want, so essentially how we, and I don't think this is properly explained here, you can very easily linking with, yeah, exactly. I'm right here. Linking with MKL. So there's a nice web page actually, and let me just show you that here. This is on our web page. It will give you, essentially, if you put in all the information about your application. I'm running on Linux, it's 64-bit. I want to have it parallel, and I want to have scale APEC or whatever. It will give you the link line, how you have to link, and will look like this. It's a long line. If you want to use standard MKL, you can just, with the Intel compiler, you can just do minus MKL, and it will use MKL. And by default, it is the parallel version. If you use minus MKL equals sequential, it will use the sequential version. So if you have on a Sandy Bridge 16 MPI threads and you want to use the sequential version of MKL, you do minus MKL equals sequential, it will use the sequential version. You have one MPI thread, want to fully utilize the full node just for gem, you use minus MKL equals parallel, and it will do the parallel version. And it will do it with the MKL num threads. I think Neil wanted to say something in the end about the Cray MKL interplay, no, Cray OpenMP interplay. Actually, this should also apply to MKL when it runs threaded, because I think there are some issues with the affinity settings for threads between Cray and Intel, and there seems to be some interference. Yeah. This is good, because this might be critical, because people might call this and they might all end up on one core and wonder why performance just screws up. Okay, just to finalize it, a couple of more components that we have in here. Of course, we have great performance. We show that here. There's for people that use C, there's a C interface to all the functions. There's C LAPEC and C BLAST, so you just prefix it with C LAPEC underscore and then the name for the LAPEC function, or if you want to call a BLAST function like dgem, you prefix it with C BLAST underscore dgem, for example, and you will get that. Scale APEC, I had already. Perdido, this is some interesting development. So Perdido is a pretty widely used sparse solver in the industry. I don't know how in sciences this is used. I think it has some roots of development also at ETH, so there might be very close ties in that. We fully support the whole Perdido, and we actually have licensed this Perdido implementation, which is given out by the original creator of Perdido. There's also a direct sparse solver interface that we supply that consumes the Perdido interface. So you can actually more or less call Perdido with a direct sparse solver, and it will call our internal solver, which is slightly different. Might nevertheless use our library, our processors more efficiently. And there's an iterative sparse solver package also that we supply within MKL if somebody needs something like that. VectorMouse library, I already had. This is essentially our implementation of libm. So all the functions available in libm are in VML, and we can, well, basically operate on vector-like structures and yield very high performance. This is performance of MKL over standard libm implementation. So it's quite high performance. VSL, this is all the random number generators. Actually, what's interesting, you can also provide your own random number generator, and it will still create streams out of it. VSL, this is a little example how something like that could be done. It's a 5-liner, right? So basically what you have to have is a stream pointer that gives you the stream of a random number generator. You create the stream, basically filling the pointer. You generate a set of random numbers. Given the size, you also, of course, have to see that and all this kind of thing. And in the end, you delete it. Again, performance numbers. As I said, a data fitting component that produces splines, for example. Right? So it's quite, and everyone who has does, well, I did it my days with numerical recipes and was quite a pain actually to do the splines. With this could be quite nice because you basically create the same way as we just had it with streams of random numbers. You create a task that does the fitting. You define which kind of fitting you want to have. Then you execute this fit in the task, and in the end you destroy the task. It's a 5-liner, and this is a full fit of a particular data set. Fast Fourier transformation. It's one of our main components, of course. It's a multi-dimensional Fourier transformation up to dimension 7, fully multi-threaded, a mixed radix implementation. What is most important is the support for the FFTW, because this is what most applications want to see is FFTW. And we fully support that. Just as a little caveat, you can't call it right away. There is a directory that contains all the interface, and you have to compile this directory. This directory comes straight away with makefile, so you just type make, and it will compile the FFTW interface, and then you call this the library created of that, and it is linked with MKL, and we call our internal Fourier transformation. Quite performant, also, of course, outperforms FFTW, which is contradiction because it's called the fastest Fourier transformation in the West. Right, this is how we use FFT. Interesting, there's a cluster FFT implementation. For most of our library functions, so for the BLAS functions, we provide a cluster implementation. For FFT, we provide a cluster implementation. So all of these, all of the functions that actually can take of parallel execution over a distributed memory system, we also provide an implementation for cluster, usually based on MPI. Partial differential equation, there's a Poisson, so now I'm actually have to think about what a Poisson equation should be. The Poisson equation is well, I don't know, I can't remember exactly anymore. Must be a second order partial differential equation. There's a Poisson library that basically has all the solvers for Laplace, for Helmholtz, and Poisson equations. I'm not quite sure what that is anymore. Which should also be able to solve problems like the one I just described before, like the second order differential wave equation. And a couple of supportive functions. Okay, I think we'll leave it with that. The takeaway actually is all the BLAS, all the linear algebra solutions, everything like that is very efficiently implemented. Additionally, of course, the fast Fourier transformations. So if you have problems like that before writing it yourself, the difference between the simple loop that I showed you, or the 3 nested loops, and MKL is probably in the order of hundredths. So if you have a linear algebra problem and try to write it down yourself, don't do it. Right? Even the original implementation of LAPAC is very low performing. So there's a couple of very highly tuned and optimized libraries which are preferable to use because you're just giving away performance if you do that. Same for FFTs, essentially. FFTW is a very good implementation. MKL has a very good implementation, but everything else is then orders of magnitude smaller already. Good. Okay. With little time left, actually, I hand it over to Mike, and let's go into OpenMP because that's one of the main takeaways for today.
So who already knows? Okay, so initially we planned for an OpenMP introduction, including some OpenMP 3.1 features. But then, you know, talking to Neil this morning, we came to the conclusion that you're not beginners and that you probably would love to see how to get performance out of OpenMP rather than to see the next Hello World program in OpenMP. Is that a correct assumption? Okay, almost everybody's nodding, so I'm not too wrong here. Okay, let's talk about hybrid, blah, blah. So the question first is why hybrid programming? And then I will show you a couple of patterns how you can actually do that. And probably the Cray guys tomorrow will complement that with some more, you know, OpenMP specific things about tasking and that kind of stuff. And then I will talk about a couple of NUMA optimizations that you can do, or at least give you an idea what you can do, and about thread pinning. This is something where Neil will also probably chime in and give you some specifics about the Cray system here. And then I honestly stole a couple of slides from a good friend of mine, from the CTO of Lawrence Livermore Labs, because he gave, at last Supercomputing, we gave an OpenMP tutorial, and I will show you his slides, so I just copied them with his permission, to give you an outlook on what it will be coming in OpenMP 4. So this is, you know, probably 3 months out, and it will be a very interesting step for OpenMP, I believe. Okay, why hybrid? So this is, you know, the typical right turn curve with the increasing core counts over time. You all know that, right? It's nothing new. The big thing here is, and this is kind of outdated numbers from Aachen University. So these numbers don't look too bad until you hit a certain level where the code actually starts to get slower again, for whatever reason, right? And the reason in this particular case is that the MPI overhead is getting significant on the node, and you know the overhead starts to get an impact and is increasing with increasing core counts, and so what you see is actually a slowdown. If you change that to a hybrid programming model, still the same curves, but now OpenMP and MPI mixed mode programming, you will see that you can get, at least in those cases where they did it on a Habertown system, as I said, pretty outdated, but still is kind of valid for today. They got over 50% improvement in runtime performance, right? Because they just avoided copying back and forth data between the local memories of the computer and all the MPI overhead, right? So hybrid programming could be a good solution for your workload as well. So use MPI for the inter-node level parallelism and OpenMP for the intra-node level parallelism. Okay, so these are basically the options that you have when you have MPI and OpenMP. So on the left, pure MPI, on the right, pure OpenMP, then hybrid, and then depending on which level of support you get from the MPI library. And nowadays, every MPI library should be thread safe. If it's not, throw it away. Is yours thread safe? It is thread safe. Ours is too, so we can say that. So basically, you should be able to do full multi-threaded communication MPI. And I'm not part of the OpenMP of the MPI forum, but I think they, in the last minute, kicked out thread interoperability in OpenMP, in MPI. So that was, I don't know why they did that. They were working on that for quite a while, and you will see what the effect is of that change. Okay, so since we now have MPI 3, most of the libraries, MPI libraries implementations should be MPI 2.1, so fully support at least querying for the thread level support, or even fully support threaded execution. Okay, let's see how we can test that. It's really easy. Instead of MPI init, you write down MPI init thread. Same syntax basically. What you give is a required level and a pointer to a variable for the implementation to store the provided level. And so what you can tell the MPI library is, hey, I want this level of threading, and the library responds with, I can give you that. And now it's up to you if you want to abort the program and say, well, sorry about that, I cannot use you. Or you can, adjust your algorithms to whatever the MPI library offers. And the levels that we support in MPI usually is thread single. That is, each MPI process just has a single thread. That's a typical multiple process single thread model. Then we have funneled. That means you have sections where the process runs parallel, but whenever it comes to MPI communication, only one thread communicates, and that's the master process. And master process in this case is the guy that executed MPI init. Then we have thread serialized. That means you can communicate from within parallel regions, but you need to make sure that it's just one thread entering the MPI library. And then we have thread multiple, which is true multi-threading. Any thread can call into MPI anytime in the execution. Okay, well, there are different support functions. For example, just in case you forgot what's the master thread, I don't know how that can happen, but you can query if you're executing from the master thread, or you can query the thread level without initializing, that kind of stuff. So there is a whole set of API functions around that to get information out of the MPI library. Okay, let's talk about master communication. That's probably the easiest one. So this is thread funnel. So only the master thread executes MPI functions. Essentially, that means do your MPI stuff, do some OpenMP stuff, do your MPI stuff, do some OpenMP stuff, do some MPI stuff. Okay, you can easily see that the downside is that you can no longer run through a whole series of multi-threaded execution without stopping the thread team whenever you want to do MPI send or MPI receive or anything other than OpenMP stuff. Okay, so this, it's kind of painful in terms of execution when you start the team, tear it down, start the team again, tear it down, just because you want to send a couple of bytes to another node. You can also do that in OpenMP. If you don't want to tear down the parallel execution all the time, you can keep your parallel region alive. You can introduce the OpenMP master statement or construct to handle all the MPI communication, and then do an OpenMP barrier to ensure that the MPI communication has been done. Then resume multi-threaded execution, and then when you do MPI again, do a master construct, do the MPI, and then do a barrier again. Quick question to the audience, why can't you use single construct? Who knows the answer? Why am I using master plus a barrier when single already limits to one thread and a barrier? Exactly, you don't know which one, and this requires that it's the master thread, so thread 0 that executes the MPI. That guy that actually executed main, right? Okay, well, this is, that's the easiest thing that you can do. It works with most MPI implementations. It should work if the MPI implementation has no clue about threading at all, but that's rather by chance. The downsides are that you always need a barrier. to ensure that MPI has finished working before you start Perl again. On NUMA architectures that have a first touch policy, the master thread touches the data when it receives it, so it will cause some serious NUMA problems because all the data that you receive through MPI will sit on one NUMA node, and probably the workers working on this data are sitting on another NUMA node. But it's easy to implement, and as I said, it's supported by most of the MPI implementations. Okay. Well, one thing, what about a global barrier? So global in this case means a barrier that synchronizes all the processes and all the threads inside those processes. Like closing down one phase of computation for all threads in the system, barrier, and then start with the next phase. And when you do that in such a hybrid program, you need to put up a barrier to synchronize all the local threads here. You need to do an OMP master to do the MPI barrier. So this synchronizes all the threads in this particular MPI process. This down here synchronizes all the MPI processes. And then you need to do another barrier to make sure that all threads see that the MPI barrier has been completed. It's a lot of barriers for just, synchronizing a couple of thousand threads. Okay. True multi-threaded communication. And this should be fixed essentially, or at least the discussion was around fixing that in MPI to make MPI better integrate with OpenMP. I don't know why they pulled out of that. Okay, multi-threaded communication. So, if you have the serialized model by your OpenMP MPI implementation, you still can call from any thread into the library, but you need to make sure that it's just one that is calling into the library, right? At any point in time, only one thread may enter the MPI library. And so the obvious solution is to put up a critical to protect all the MPI primitives. And it would be good practice to have an own critical section for MPI, so use a named critical to ensure that the MPI criticals are not interfacing with any other criticals to protect other data structures. That gives you a little bit more parallelism, but still, you need the critical or some locking. You can also do omset lock, whatever calls, but you need to have a critical section around the MPI stuff. Okay, well, it's better, of course. The lock operations usually are not as expensive as a barrier operation because it affects the whole barrier affects the whole system of threads. A lock can be slightly less, but still you flush the cache. You still have limited parallelism, and on NUMA architectures, again, you have the problem that one of the threads touches the data by receiving it, and the others need to compete for the same NUMA node. Okay, and then fully parallel, well, that's supported, as I said, by most of the MPI implementations now. You can call MPI functions from any thread from anywhere in your parallel regions. Okay? That's actually what you want, right? So whenever one thread wants to communicate, it can just do that. The only problem is, how can you send a message from this guy over here, so OpenMP thread A on node 0 to OpenMP thread B on another node? So how can you address OpenMP threads? There you go. Okay, so the problem is as follows. You got this network, you got the individual nodes, and you got a address space from MPI from 0 to P. That's the number of MPI ranks that you have. And then, for the sake of simplicity, I would assume that if every process has the same number of threads, and then inside a node, you get another level of numbering from 0 to T, with T being the number of OpenMP threads in that particular process. Okay? The problem now is that the OpenMP thread IDs that you have are first non-unique, and MPI doesn't recognize them, right? And exactly as Chris already mentioned, just use message tags to color your messages with the MPI thread IDs. looks like that. So you do an MPI send, and here in the tag argument, you place a thread ID. Right, that's the local thread ID for the sender, right? And if you want to receive a message, you would use omp get thread num to tell MPI to receive exactly messages with that tag, meaning for this particular OpenMP thread. Okay, this has some consequences on reordering messages and puts a burden on the MPI implementation, but still it works. And it kind of works with kind of a good performance. Okay, the only thing is, what do you do if you want to use message tags for your algorithm? Some MPI implementations actually make use of the tag, of a message tag, to distinguish control messages from data messages or solver messages from DGEM messages, whatever. So what do you do then? Exactly. You need a dirty and really ugly hack. What you do is you define a couple of macros. You can do that in Fortran as well. But I'm a C guy, so that's why I'm using macros here. So what you do is you take this thread ID, you take the tag, you shift the thread ID by 16, and then add the tag to the resulting bit mask. So that gives you 16 bits for the tag and 16 bits for the threads. Should even work for us for the next 10 years, probably, in terms of thread IDs. Okay, and then when you do, when you want to get the message for a particular thread, you take omp get thread num, shift it by 16 again, and then add the tag. And this way you can merge the tag ID and the thread ID into a single variable and get this information back out. Okay, and you can easily adjust it. So whenever you're not satisfied with having 32K different tags, you can still shift by 17 or whatever. Okay, you can easily adjust that. Okay, still, we got the same problem. When we do an MPI barrier, we need to protect it with a critical or a master construct because it's no good idea to have multiple threads calling into an MPI barrier. This will break semantics. This will not work. Yep. Yep.
Sure it works with critical. I thought the semantics of critical was that no one can be in there more than one can be in there at the same time. But if the second one arrives.
Well, you need to do not single, not critical, single or master. You need to ensure that this is executed exactly once. Right, not with critical. Sorry. Yeah. Good one. Thanks for listening. Okay, so the good, in this case, the code would execute as many barriers as you would have parallel threads. So this is not a single MPI barrier, but this is 16 or 8 per process. Yes, and it's not well defined what happens when multiple threads from one process call into the same MPI barrier. Yes. Anything can happen, including a little leprechaun sitting on your chair. Okay, so the good is OpenMP and MPI blend kind of well if you respect certain rules, right? It can help improve performance. I'm not selling this as the rule of thumb. So when performance is bad, take OpenMP and MPI in the same program, and it will boost your performance by 50%. Okay, it's an option, right? It's particularly an option when you see a lot of MPI overhead coming from the local node, communicating back and forth between the cores of the system. Okay, you always need to be aware of the issues that you have. Not all MPI implementations are still thread safe. Most of the important ones are, like Cray, Intel, OpenMPI, Web Page, whatever. So most of the grown MPI implementations are. The ugly thing is that you always need some workarounds to make things work, especially when you have complicated algorithms, what you typically have, right? It's not Hello World that you are working with. And the other thing is, what is the best setting for processes per node and threads per process? So is the sweet spot having one single MPI process per node, and then, you know, filling the system with threads? Is it one MPI process per socket, or NUMA domain, and then fill up the NUMA domain with threads? That's probably the best initial guess. Or is it 2 threads per socket? You know, there's a lot of additional optimization potential in the search space of finding the right tweaks for your application. Okay, NUMA optimizations. Well, the problem with NUMA is that we have something called first touch policy. That means that when you implement virtual memory on a modern operating system, and you can try that yourself, just write a little program with a while loop and do a malloc of 4 kilobytes and let that run. It will run long, and you can do the math. It will allocate way more memory than you have physically installed in terms of RAM, and that you have physically installed in terms of swap space. You can allocate terabytes of main memory with that. But the problem is, as soon as you start touching it, at some point when you fill up the main memory and the swap, the program will blow up. But you can allocate terabytes of main memory just, you know, by mallocing 4K pages. Okay, and the reason is that malloc is implemented in a way that it just gives you a guarantee that you get a unique pointer into the main memory. It doesn't guarantee that the memory has actually been allocated when you call malloc. And typically the operating system just returns you a new pointer, and the first time you access that pointer, either by reading or writing, the page gets allocated on a physical page, right? That gives you a page fault, right? Because the page is not in the virtual memory, and then the operating system will detect, oh, I didn't have a physical page for it, and will allocate one for you, right? And then, you know, you have a physical page either in memory or swap. Okay, now the operating system, if you have a NUMA machine, that is different memory modules attached to local CPUs, the NUMA node that executes the first memory access will get the page. So if it's core 0 or node 0, the page will be in the local memory of that particular socket, right? And that's difficult because, you know, at least most versions of Linux don't support page migration yet. So whenever this page has been allocated on a certain memory module, it will stay there almost forever. Okay, the only thing is that you force the system to swap, and then there's hopefully a little chance that it gets swapped in somewhere else, probably. Okay, so what's the deal about it? Well, actually none. It's still memory. But the thing is, if you do something like that, so you initialize your data in one thread, and then you do some parallel work, actually working on the data that you allocated, what you get is that the CPU that executes those 2 loops gets all the memory, and everybody else in the system is going to that particular CPU asking for the pages and for the memory transfers to get the data from the allocation side to the working side. Okay, and the idea here is that you actually also always parallelize the data allocation loops in the same way as you parallelize the worker loops. And this gives you a local slice of the allocated memory on each node so that all the local threads go to the local main memory. Okay, for a matrix vector multiplication, this is nice, easy, and happiness, right? For a real application, this can be a tough job. And that's probably why having a MPI process per NUMA node is a good idea, because then it's ensured that whenever you receive a message in this MPI process, it's on the right local node. That's the idea behind that.
The first loop and what happens in the first loop?
Here? Yeah, that's just malloc and allocation. Right? You touch it the first time, like reading in everything from file or receiving it from another MPI process.
It's required to have 2 loops.
Well, in this case, it's required to have 2 loops because we are initializing a matrix, right? But you can also have a single loop if it's just an array, or you can have 3 loops if it's a cube or whatever. So this is just some code that initializes the data, and this is just some code that works on the data, right? And in your particular cases can be arbitrarily complex. Okay, so having said that, MPI processes are in the same ballpark. They are suffering from the same problems. So that means, for example, a process allocates memory on one NUMA node, and then all of a sudden the OpenMP, the operating system, decides to move that process to a different NUMA node, right? Or same can happen with a thread. So whenever a thread allocates data, it might be wandering around in the system. And of course, when you do internode communication, so sending one MPI message to another MPI process on the same machine, you might see different latencies compared to other processes, right? So messages are slower than others. And the other thing is, there is a thing called file system cache. That's also a fun thing. So whenever you write something to disk or you read something from disk, the operating system stores a copy of that in main memory for faster access. And typically, the file system cache is residing on one NUMA node, right? And so there might be NUMA nodes in your system that are fuller than others, right? And then, you know, things start to get complicated. And also, when you read a file from a process, and then the file system caches on the NUMA node, you also see different latencies as you would see when you access the file more locally from that NUMA node with the file system cache. Okay, thread pinning. So thread pinning basically means that you tell the operating system to not move around threads or processes. So initially, when you start a process, the operating system is free to start it anywhere on the system and move it around as needed, right? It might destroy a NUMA locality, and it might also affect performance, because whenever the thread is migrated to another core or another socket, you lose cache locality and that kind of stuff, right? Let me show you a little example on what this might actually mean for an MPI application. Let's say you got something like a Gauss-Seidel solver or a Jacobi solver or whatever, and typically those exhibit such a nearest neighbor communication, at least in the one-dimensional decomposition. That means this guy is talking only to this guy is only talking to that guy, right? Now, if you allocate that on a real machine, you would have two compute nodes, right? Node 0 and 1, and each of those compute nodes, if it's Sandy Bridge or Westmere machines, will have two NUMA nodes, 0 and 1, 0 and 1. And now if you do a wrong thread placement, you get a communication behavior like this, right? So this guy here is communicating to that guy, sending over the QPI link, which is rather low memory bandwidth and high latency compared to the local memory, right? Same for this guy here. This guy is talking to that guy. So those two pairs of processes are always competing about the same QPI link. If you change the allocation like this, everything is just perfect. This guy is talking locally to that guy. Okay, those two guys need to talk to each other. Those guys are talking locally. Those guys are talking over the InfiniBand interconnect, and those guys are again talking rather locally, right? And this gives you performance. Okay, how can you achieve that? The easiest way is the task set command. It's really easy. Task set, pinning mask, program. Let's say it starts 4 OpenMP threads. If you do bit mask 1, 0, 1, 0, 1, this is for core 0, core 1, core 2, core 3, core 4 on the next socket. So this would give you that kind of thread placement. It's like scattering the application process across different sockets and different cores. Okay? And by the way, this is the bit mask for 85. Okay, so for each processor in the system, we have a bit. and if the corresponding bit is set, the operating system may schedule a thread of this particular process on that processor. Okay, if you do the same mask, and now this is where it becomes complicated, or you need to be aware of it at least. If you start a program with 8 threads and keep the same bit mask that only allows for 4 execution cores, you will end up in a scenario like this. Right? Because you only allow the operating system to execute threads of your application process on those 4 cores, and it will stick to it. And if you create more threads than you have cores allowed, you will end up with half the performance. Right? Because you essentially forbid the operating system to move that guy over here. Okay? Little caveat, keep that in mind. Okay, you can also do logical core numbers instead of bit masks. So -C 023 would use socket 0 completely. And if you execute another command, you would, with a different set of cores, you can force the second application to the other CPU socket. Okay. By the way, some queuing systems, and I think on the Cascade system this is done, automatically try to provide such commands, or at least give you some indication what are the reserved CPUs. Is that correct?
Well, the launcher, which is MPI run,
Yep.
takes care of this.
Okay, right. So this is, how you would do it manually on any system, and typically well-engineered systems already provide that from the environment automatically. Okay? Yeah.
Are you going to talk about the helper thread?
No. No.
So how does this interact with the helper?
In our implementation, it does interact, but the helper thread usually doesn't do anything big in terms of performance. It's not continuously spinning and consuming cycles.
Yeah, but so this just says use one of these
Right.
cores. It doesn't pin them to the core.
Exactly. So this is, the operating system is still free to schedule those guys around as desired, only on those 4 cores. So it still can switch them around, but it will kind of stick to that. So the operating system is smart enough to not move them around. It's not a per thread pinning. Right. We will come to that. Okay. Okay, you can also do that from inside your application. This is just to show you how to do that in C code. So this now explicitly pins OpenMP threads to a single core, right? So what we do is, there's a library called PLPA, whatever that means. You specify an array of cores, then you do your parallel region, you start all the OpenMP threads, and what you do is, you index into the core array, you get the ID of the core you want to run on, and then you set up a mask that exactly has 1 bit set corresponding to what you selected down here or up here, and then you call into this PLPA library to call set affinity, that's an operating system call, and then this is pinned to whatever you selected. Okay? This is how you would do it manually. And of course, there are better ways to do that. It's just to show you how this works internally. You can do that in MPI as well. So you can start up your MPI communication, and then you can pin the process to a particular core on the system as you desire. Okay? This is just to show you how it works. I'm not saying that you should actually implement that. Okay, the easiest way to do that, and Cray MPI has a similar means, is to tell the MPI library to do that for you. So basically what you tell MPI run is to turn pinning on in the MPI library. You can also ask, at least our implementation, with MPI debug, to tell you what the pinning is that has been selected and what the fabric is you're running on and that kind of stuff. And so, for example, if you tell our MPI library to do IMPI pin procs to 2, 0, 2, 4, and 6, you will end up in the same scenario as in the task set command, but now this guy is firmly pinned to core 0. It will not wander around in the system. Okay? Now, if you do 8, same pinning mask, you will end up in the same scenario again. Okay. Yeah.
So this, your MPI library is smart enough to skip the complete thread?
Yes. Well, the MPI library doesn't have a helper thread.
Oh, this is not threading.
This is just MPI. We will come to threading as well. Okay. How do you find out the structure of the system? We ship a little command called CPU info with our library, with our MPI library, and you can also use that for OpenMP pinning, of course. But it's part of the MPI. It will tell you how many CPUs, logical CPUs you have, how many packages or sockets in the system, how many cores per package, and how many threads per core. Right? So this is the general statistics of the system. Then it will tell you which logical processor is on which package, on which physical processor, and which hyperthread on this physical processor. It will tell you for each logical processor which thread ID, on which core, and which package this is. So this is, the first table turned around. And then we have the placement on packages. So that means on package 0 you find these cores. On package 1 you find these cores with those logical numbers. And the parentheses indicate the same hyperthreading infrastructure. And down there you see the cache structure. So those guys here share the same L1 cache. Those guys here share the L2 cache. And those guys here are running on the same L3 cache. Okay, so this is easy to detect. Also the sharing behavior between your processes on the physical system. It's quite neat to do that. Okay, thread affinity, same issue. And we have a environment variable called KMP affinity that controls the setting of OpenMP threads. Right? It's a vendor-specific extension to OpenMP. I will come to that in about 10 minutes or so. So this is vendor-specific, and we are right now defining a standard way to do that. Neil already told me that this kind of conflicts with what Cray is supporting through the app run command, right? So there are some interaction problems.
I never tried this, but with this AP run, you can either have a run control the placement in Affinity, or you can say AP run no, that doesn't do anything.
Mm-hmm.
At that point, maybe this is just fine.
Yeah. So there.
It might be helpful and useful also now.
Okay. Okay. But I think Neil, you got some slides on that you're going to present. Okay. So what you can specify, for example, granularity, fine, and compact. So we have logical names for typical thread placements. Compact means keep the threads as close together as possible. So start filling a local cache, then the socket, and when you run out of cores on the socket, take the next core. Right? We also have scatter. That would place threads as far apart as possible. So start one thread on the local socket, then do the next one on another socket, right? Then another socket until you run out of sockets, and then you come back to the first socket. And if there is cache sharing on this socket, try to avoid cache sharing as much as possible and use some other shared cache, right? So we try to keep those. It's like Germans coming to a restaurant, right? If there is a free table right in the corner, far away from all the other guys, a German will sit right there. Okay, and only if the restaurant is completely filled up, they will start, joining our more tables. I'm German, I can make that joke. Okay, we also have verbers. In this case, KMP affinity reports what is the OS to processor mapping, and then it will tell you what OpenMP thread is bound to which operating system thread. And this takes care of the control thread. Okay, references. This is actually a very nice book by Hager and Verlan, Introduction to High Performance Computing for Scientists and Engineers. It's well written. It doesn't tell you how OpenMP works or MPI works. it tries to give you some good overview on how to do performance optimization. So it's really, I'm not getting any money from them, but it's really a good book. Okay. Okay, now I'm converting myself to Bronis de Subinsky. He's Chief Technical Officer of Lawrence Livermore National Labs. We did a tutorial at Supercomputing 12. We submitted an OpenMP tutorial for International Supercomputing 13 in Leipzig, and we are also applying with that kind of tutorial for Supercomputing 13 again. And he kindly agreed that I can steal his slides and present them to you. Because they contain a good summary of what is going on with OpenMP and what you can expect during the next couple of months. Okay, so this is the status at Supercomputing 12. So what we did is, with OpenMP 3, it took us about, I think, 5 years until we came up with a new specification. From then, a minor release like OpenMP 3.1 took us 3 years to complete. And this is, not as fast moving as some of our users would like to have it. It's like C++. You were waiting for C++ 11 for almost a couple of years. Too long, basically. So what we did is we switched to a new time-based release process. So we tried to get a new specification out every year, or probably every 2 years. And everything that is ready at that point in time will make it into the new release. And if it's, shiny and glory and something really new, we will call it OpenMP 5. And if it's not, we will call it OpenMP 4.1. That's the idea behind it. So to avoid gating issues that hold up the specification for just too long. We also switched to a new process in terms of that we now release a release candidate. We have RC1 out since Supercomputing 12. We planned to have RC2 release candidate 2 out by mid of February. Unfortunately, that slipped to mid-March, so it should be ready quite soon. Okay. Then we will do a public comment draft where everybody of you guys can comment on what you like in the specification or can give feedback. And then we will come up with OpenMP 4, hopefully ISC timeframe. So International Supercomputing or Supercomputing at latest. Okay, and then we will start immediately with OpenMP 5, or that's the working title. It could also be OpenMP 4.5 or whatever. Okay, so what's new? The first thing is OpenMP has been a threading model, but we've seen that current architectures exhibit multiple levels of parallelization. We have MPI or cluster level, we have node level, multi-threading, and we have SIMD parallelism. Right? If you look to a graphics card, you also got kind of SIMD parallelism. And so we tried to fix that by coming up with a vendor agnostic standard way of specifying how to do SIMD vectorization. So what you did in the vectorization lab with our compiler specific, Intel specific pragmas now is part of OpenMP. So no matter what compiler you use, it hopefully will recognize, if it's fully compliant, those pragmas and create SIMD code out of your SIMDized loops. Okay? It's kind of the same thing as we have in our compiler. The names have changed slightly. It contains more features than we have in our compiler. So, for example, our compiler just offers private. And similar to what OpenMP does for work sharing, we also offer last private reduction, collapse. First private is still in discussion, for example. But we support a bit more than what we have in our Intel compiler at the moment. Okay, but basically, it transports SIMD into OpenMP. There's also pragma omp declare SIMD and to declare a SIMD version of a function so that you can call those functions out of a SIMDized loop. Basically, it's the same type of pragma, but not based on loops, based on functions. There's also SIMDized work sharings. That means the SIMD version, the SIMD pragma, as on 2 slides ago, will just affect a single loop and will still execute this single loop sequentially, but with SIMD parallel instructions, right? And this also adds threading to the SIMD pragma. That is, we will execute a SIMD loop on multiple threads. It's a work sharing construct, as you know that from OpenMP already, but now with SIMD added to it, right? And the implementation is free to choose how SIMD and threading interact together for best performance. We also have this parallel for SIMD. So this is a work sharing construct, and this adds thread creation to the work sharing construct as well. Okay, this is an example how you can apply that. So you got this pragma OpenMP SIMD for the min function. So what the compiler does is it automatically creates a function min with a SIMD version where a and b are no longer scalar floats, but SIMD vector floats, right? Like an AVX register A and an AVX register B. Okay, and this will be a vectorized if statement with a vectorized return that returns the result of the min computation. Okay, or you can have, let's say, a distance square root function that executes multiple instances of x and y at the same time and computes some Euclidean distance, whatever. Okay, and then you can call those min and disksq functions from a SIMD loop. So this is, executing in chunks of 4, in SIMD chunks of 4 for AVX, and it would, 8, and it would call the vectorized version of min and disksq. Right? This already works in different flavors in different compilers. So our compiler, for example, has a vectorized version of the sine functions, or cosine, or exponential, or square root. And this adds the same feature for user-defined functions, right? To just increase the potential of vectorization. Okay, what else? Pinning. Pinning is a pain in OpenMP because it's essentially not defined. So every OpenMP vendor does something different. We have KMP Affinity. Cray has some pinning features, I believe. IBM has theirs, Oracle, whatnot. So everybody does, whatever they like. And then it comes to an interaction between the execution environment, like AppRun in the Cray system, and our OpenMP library. And I can completely understand that Cray, for example, is not supporting any pinning methodology in OpenMP implementations on this planet. It would be hilarious to do that, right? And so that's where, our OpenMP runtime cannot speak to the Cray runtime system in a way that the problem is actually resolved, right? So with OpenMP 4, we will fix that. We already introduced multiple thread nestings or multiple thread number specifications in OpenMP 3.1 to support nested parallelism. So this means the first level of OpenMP parallel regions will get 4 threads. If these 4 threads create another parallel region, it will create 3 threads. And if those parallel regions will again create parallel regions, they will only receive 2 threads. We fixed that in OpenMP 3.1. That was a major step already to make nesting possible or easier to use. And now with OpenMP procbind, we actually specify a standard way to describe pinning. Right? So the operating system or the scheduler, the batch system, whoever, can interact with any OpenMP implementation in a standard way. This is a major step. Okay? And it also involved a lot of discussions. Okay, in OpenMP 3.1, we had OpenMP procbind and true false to just enable or turn off pinning. And now we are adding a major feature to actually describe how you want to do the pinning. And this is done through so-called places. So you know what, we don't want to talk about cores, sockets, logical cores, logical threads, SMT. You know, there are so many different names out there from different vendors that we had to come up with a completely new naming convention. And places was, you know, it's a place where you can execute something. That's why we come up with places. And you can specify abstract names like threads, cores, and sockets, whatever they mean for the system you're running on. This is not defined, right? So this can be something like a true socket in the system. It can also be just a part of the socket. It's up to the implementation to define that, because it doesn't make sense to speak about sockets in any system on this planet, right? Okay, there are also clauses that we add to the parallel construct where you can specify where you want to bind your threads that come from this OpenMP region to. And we also got, of course, runtime support functions to query the current status of binding. So what this means is, let's say you start your initial application with a single thread, right? And you get several execution places, and the circle here means that the thread is actually executing on one of those slots, right? Now, if you create a parallel region, you can say spread across the system. So we would start spreading out the individual processes, binding them to a particular core on the system, right? So this can be packages or real processors or whatever, right? And then on the next level, you could specify, now keep everything close together, because now we are really working on tight data. We have communication between the threads. We need to keep them close together as possible. Okay, and then you can, on the initial level, you spread out when you create the first parallel region. On the next level, you keep the threads close together to save communication costs across QPI links or across the system. Okay, and this is described in a standard way, so that anybody outside, without knowing how we implement it internally, can actually make use of that and give us the right information about which cores we can actually utilize for an OpenMP program. Okay, reductions. Reductions are fun in OpenMP because up to OpenMP 3.0, we only supported arithmetic reductions, like plus, minus, multiplication, division, that kind of stuff, and or, you know, a couple of others. With OpenMP 3.1, we introduced min and max in C and C++. Fortran had it for many times, for many years. C++ didn't have it. Users were forced to implement ugly workarounds to get a min reduction implemented or a max reduction. We fixed that in OpenMP 3.1, and this in OpenMP 4 will be the major thing. What you can do now in Fortran and C++ is you can provide your own user-defined reduction no matter what it does. Right? You're not restricted up to the predefined set of things that are in the specification. You can declare a new reduction identifier on certain types with a combiner function. Combiner function means take two elements, reduce them into a single one, and do that until you get a final single result. That is the global result. And you can specify an identity element. Okay, so that's the neutral element for this reduction operation. So what you can do, for example, and this is C++, wonderful C++ code. You can now declare the reduction merge that is working on a standard vector of integers. The reduction operation is take what is coming from one of the OpenMP threads, what is coming from the other OpenMP thread, and insert all that into a standard vector. So you'd reduce two standard vectors into a single standard vector. And then the runtime system will take care to apply that in a certain fashion to reduce all the partial results of all your individual threads into a single standard vector. Or you can do, well, and how you apply it, it's really easy. You can now specify what you define here as a reduction identifier. You can use down here in the reduction clause where you used to have plus, minus, multiplication, and that kind of stuff. Okay, Fortran 2003. I already commented earlier on that. OpenMP 3.1 was based on still Fortran 95, I believe. And we added a couple of features that we are now supporting in Fortran 2003, so that now all Fortran 2003 compilers can also support OpenMP 4 without breaking either semantics. Okay. What else? We have task group. That's also new features. Now you can group individual tasks that you create from your parallel regions into logical entities or groups. And then at the end, you can form a barrier that affects the whole group. Before that, you had task create, task wait. And now if you put up a task group, you can save all the task waits because the task group will implicitly wait for all tasks to complete that are belonging to this particular task group. Okay, and one feature that is not in there because it's not in a true OpenMP HPC feature, we also support cancellation of parallel execution, and this is also tied to the task group feature. Right, so whenever you fire a task cancellation, it will affect all the tasks in a particular task group. This is basically syntactic sugar. You could do that in OpenMP 3.1 as well, but it's a lot of work and a lot of programming stuff that you need to write down. What else? In OpenMP 3.1, we introduced new atomic operations like atomic read and write. We now allow to atomically capture a value. And this is needed when you implement kind of a scheduling algorithm where you need to switch to the next element, but at the same time you need to know which element you need to process. Right? This is what the OpenMP implementation basically does for dynamic scheduling of work shares. And if you want to implement something like that by yourself, you need an atomic capture. You couldn't do that in OpenMP earlier versions. Now with OpenMP 4, you can do that. Okay, what else? We have support for accelerators. That is NVIDIA GPUs and Xeon Phi coprocessors. Basically, what you can do is you can write down a pragma to offload computation to an accelerator or coprocessor. We are going to also add new features in terms of supporting or fully supporting Fortran 03. We are also working on task dependencies. Actually, they have almost made it into the standard. So they passed all the votes, and we are now implementing that for RC2. So now you can specify execute this task only if this task has finished. You can do that today, but it's a pain. Right? And now you got nice clauses to do that. Yep. No, it works through input and output clauses. It's basically data-driven. So you're specifying this task needs A, this task produces A, and so this task has to wait for that one. That's the way it is done. Okay, and even that's OpenMP 4. Future looking in the future, what we are discussing for OpenMP 5, 6, 7, and 8, and whatnot. So we are talking about adding support for memory affinity so that you can tell, for example, a task, please execute locally where your data is, so that you can further influence the scheduling decisions. Of course, the new accelerator support needs some refinements. When we come up with the first version, there will be additional features that we need to talk about. There is some group looking into transactional memory support and thread level speculation. So for example, IBM has transactional memory, Intel has restricted transactional memory. So this might be something that might be visible in the programming language since now the hardware supports it. We are also looking into additional task and thread synchronization methodologies where you can suspend threads or do something like POSIX thread program. We put one thread asleep and schedule another one for execution. We also need to extend OpenMP at some point in time to the new base languages. So that's C99, C++ 11, Fortran 2003, and Fortran 2008. Interoperability and composability is a big deal. One example where this essentially, I'm not saying goes wrong, but at least needs some attention by the user is when you link MKL into your program that is also OpenMP parallel. Right? You need to take care that you don't call too many instances of MKL or use the sequential version of MKL or how that blends with your OpenMP. And this tool, this thing down here gained a lot of traction over the past 6 months. This is basically specifying a standard way to hook a tool to the OpenMP library to investigate what's going on the OpenMP level in terms of performance, like timings, profiling, debugging, that kind of stuff. Phew, that's it. That's the OpenMP 4 outlook. As I said, RC2 is about to be expected in a week, probably, and then the final version will be coming about 2 months later. Okay, thanks. Questions? Silence is a no. Okay, well, thank you. What's next? Hands-on. Okay, so we have a couple of OpenMP hands-ons. You can also continue with the library hands-on or any other hands-on that you didn't do after lunch. We will be around until 6, I guess, roughly, plus minus 5 minutes. Okay.
Don't generate random numbers piece by piece. You generate streams of random numbers. And if you have written a Monte Carlo, you know that random number generation can be a performance critical issue. You sometimes spend more time in generating the random number than actually doing the step. So this is quite nice for that. There's also a summary statistical library that allows all kind of statistical computation like skewness and kurtosis of matrices and so on, error calculations, all these kind of things. There's a component that does data fitting. It does all kind of splines and all these things and everything nicely tasked and so. There's a number of solvers for partial differential equations. These guys actually do exactly what we tried to program in intrinsics. It does Poisson equations, it does Laplace equations, these kind of things. You can basically, if you have like the wave equation is nothing like a twice time-dependent Laplace equation, so you could wrap this into one of these solvers. Right, so that's essentially it. Okay, we support that for, of course, all possible data types, single real, complex precisions. It's available for C, C++, and Fortran mostly. For some packages, the Fortran interface is the natural one, like LAPAC. And there's access via a function library called CBLAS, which allows the access to these functions from C. Of course, like on the Intel Web Page, you find all nice knowledge base and forums and documentations. I think there's even a full forum about MKL. Quite popular. Okay, and this is minimum interesting. Okay, so now the components in detail. I already talked about that. All blast levels, of course, are highly vectorized. This is important for us internally because we try to reach peak performance on the blast, and this is critical component for most deals. essentially LinPack on all these kind of things rely on our performance in MKL, especially the level 3 BLAS. The matrix operations are essentially very critical. As I said, sparse BLAS is fully supported. There's a full packed and banded storage of matrices, and of course the corresponding routines to actually solve that. Well, this is actually the explanation of what we would have done in the hands-on. This is a matrix multiplication. Right? That's very nice. A lot of people write it that way. This would be an implementation in BLAS level 1. D dot basically means a scalar product between two matrices. So you do square many scalar products. Then essentially from the BLAS level 2, you can wrap that further back into matrix vector multiplications. And then you basically have n many matrix vector multiplications. Or if you just do away with anything, you just have the function dgem, which does the whole thing. So this is essentially what dgem does. Of course, it doesn't do it this way. It does it in a very nice cache-blocked way, so you get top performance out of it. Don't expect, and we had this this case recently, exactly here. Don't expect performance out of matrices smaller than, say, 12. Because for small matrices, this is not going to work. This is set up for bigger matrices. Close to peak performance, like reasonable fractions of peak performance, you get with matrices in the order of hundreds and thousands. Right. LAPACK, anybody highly depending on LAPACK and BLAS? A lot of people actually should use that. Nobody has a linear algebra problem? Top 500 is not exactly a problem, actually. It's a nuisance. Okay, so I thought that this is fascinating. No iterative solvers, something like that. Or top 500 is just matrix multiplication. It's just a, oh, this is good. Okay. Huh?
The director of the site actually has a problem that is heavily utilized as a gem. From a short distance.
Oh, good to know. Well, he should be happy with dgem actually, with our gem. Okay. Okay, so basically MKL supplies everything that's in LAPACK. LAPACK is a pretty extensive set of solver and utility functionalities. Everything that's, so for my personally, I usually do that with eigensolvers, and they are pretty nicely performing on MKL. Additionally to that, we have kind of, what's really cool, we have callback functions. We put that in, so software vendors that actually run through a big calculation could actually feedback into the GUI of the user where they are. How much do we still have to do? That's why there's a callback function. So you can basically get a feedback on where the computation currently is. The whole of that is actually, if it is possible, it is parallelized completely. So all of BLAS, of course, is fully parallelized. So if you give MKL a node with a number of cores, it will fully utilize that node whenever it's possible. It would, by default, just do it.
How do you give it a node?
You just started. You link it. So, okay, that's a very good question. Okay, so you can control. Let me just jump here a little bit to the environment settings. All right, so essentially it would read out these variables. All right. OpenMP num threads and MKL num threads must not be the same thing. You can set MKL num threads, and it will use those num threads. So this is basically what MKL provides, the feature set, basically. Well, first of all, there's, of course, BLAS, basic linear algebra subroutines. Everything that's connected with multiplying vectors, multiplying matrices and vectors, and multiplying matrices and matrices. This is the BLAS levels, 1, 2, 3. So this is all very highly optimized, what we have here. Additionally, there's a sparse BLAS implementation that we provide. And of course, the linear algebra package, all the solver functions, eigenvalue solvers, Cholesky, whatever. Everything you desire, everything you know from LAPACK, we implement in this library as well. Standard calling interface, no problem. Then there is a scale APAC for distributed memory architectures. So I have a couple of workloads requiring that. It's quite nice software package. Of course, there is FFTs. And I'll just mention it later on again. There's also, so we implement our Fourier transforms ourselves. However, we have interfaces into the other public and most publicly accepted fast Fourier transformation package, which is FFTW. So we provide an interface package into FFTW, which calls our internal Fourier transformation. There is a cluster FFT solution, which I will not speak too much about. And there is this dense, sparse matrix solvers, Perdido, DSS, and ISS that we also supply. In the MKL is also a VectorMouse library. This, I think, also already comes with a compiler. If you use our compiler, you already have a vectorizable mouth library. Often leads a little bit to irritations because this will essentially call vectorized versions of exp, power, Zenus, and so on. There's a vector statistical library. This is basically, mostly of it is a huge collection of random number generators, and which can be different from OpenMP. You can have many OpenMP threads, like say 8, each using 2 threads on MKL. That will work. So you have OpenMP num threads. If you don't set MKL num thread, it will just use the OpenMP num threads. If you set MKL num threads, it will use MKL num threads. So that could be, that's, if you don't want, so essentially how we, and I don't think this is properly explained here, you can very easily linking with, yeah, exactly. I'm right here. Linking with MKL. So there's a nice web page actually, and let me just show you that here. This is on our web page. It will give you essentially, if you put in all the information about your application. I'm running on Linux, a 64-bit. I want to have it parallel, and I want to have scale APAC or whatever. It will give you the link line, how you have to link, and it will look like this. It's a long line. If you want to use standard MKL, you can just, with the Intel compiler, you can just do minus MKL, and it will use MKL. And by default, it is the parallel version. If you use minus MKL equals sequential, it will use the sequential version. So if you have on a Sandy Bridge 16 MPI threads and you want to use the sequential version of MKL, you do minus MKL equals sequential, it will use the sequential version. You have one MPI thread, want to fully utilize the full node just for gem, you use minus MKL equals parallel, and it will do the parallel version. And it will do it with the MKL num threads. Right. I think Neil wanted to say something in the end about the Cray MKL interplay, no, Cray OpenMP interplay. Actually, this should also apply to MKL when it runs threaded, because I think there are some issues with the affinity settings for threads between Cray and Intel, and there seems to be some interference. Yeah. This is good because this might be critical because people might call this and they might all end up on one core.